Namaskar, welcome to the channel Anka Anand Aharan, that is extracting happiness from the teaching learning process of mathematics. Today one of the significant aspect of linear algebra, that is vector space, will be discussed. Before discussing vector space, let us know what do we mean by an operation is defined on a set. Suppose V is a set and I write plus. That means if you take any two elements of V, let us take U and W belongs to V, then U plus W should also belong to V. If this is true for all the elements of V, then we used to tell that this operation plus is well defined in V. For example, set of natural number, there my set of natural number, my addition operation is well defined. You add any two natural numbers, again resultant is a natural number. But subtraction is not well defined on set of natural number. For example, 2 minus 5. This is a natural number, this is a natural number, but the resultant is minus 3, which is not a natural number. That implies n is not closed under minus symbol, or minus operation is not defined on n. Okay, so this is all about an operation defined on a set. Now consider V is a set having two operations defined on it. It is addition and scalar multiplication. Now any set having some operations defined on it is said to be a structure. It is said to be a structure. And any structure V having vector addition and scalar multiplication property operations defined on it is said to be a vector space if these 8 properties of addition and scalar multiplications are satisfied by that V or by that structure. First property is, in this space or set, vector addition is commutative, means the addition is commutative. It is commutative. Similarly, addition is associative. X plus y plus z is equal to x plus y plus z. It is associative. Additive identity exists. There exists an element 0 belongs to V for all x belongs to V such that x plus 0 is equal to 0 plus x is equal to x. This 0 is said to be additive identity. This is additive identity. 0 vector is additive identity of any set V. Then 4. Additive inverse. For all x belonging to V, there exists minus x belonging to V such that x plus minus x is equal to 0. So here this is additive inverse. For example, additive inverse of 5 is minus 5. Multiplicative inverse of 5 is 1 by 5. Multiplicative identity is 1 and additive identity is 0. Okay. So with these 4 properties and 4 properties of scalar multiplication, what are those properties? It is 1 into x is equal to x, 6, C1, C2 whole operated with x gives me C1, first C2 is operated, then C1 will operate on it. it. Similarly, distributive. How? C into x plus y is equal to cx plus cy. Last property, that is c1 plus c2 whole into x is equal to c1x plus c2x. Any set V of having two operations addition and scalar multiplication satisfying these 8 properties is said to be a vector space. If these 8 properties are satisfied, then V is a vector space. So there are several vector spaces. For example, R square, R cube, R4, R5, R, all these are vector space. Examples of vector spaces. So they satisfy all these 8 properties. But in most of the cases, we collect or take a subset of a vector space. And we want to study whether that subset or subcollection of the original vector space is a subspace of it or not. Whether it is a vector space by itself or not. So for that we need not verify these 8 properties. Suppose given that V is a vector space. Let V is a vector space. And W is a subset of V. Then W is a subspace. And it itself is a vector space. If W is not empty, that is 0 vector belongs to W, W is closed under scalar multiplication and vector addition. For all U V belongs to W, U plus V belongs to W. This is closed under vector addition. It is W is closed under vector addition. Similarly, third property is for any U belongs to W and scalar C, for all scalar C, Cu belongs to W. That means W is closed under scalar multiplication. Okay, W is closed under scalar multiplication. With these 3 properties, it is if and only if. Means if it is these 3 properties are satisfied, these 2 properties can be combined together to tell W is closed under linear combination. These 2 properties together it can be decided or claimed, but we will make it 2 independent so that in simplified way we can solve or prove. Okay, so now the question is, what about a vector space? So if any V associated with the 2 operations defined on it, that is vector addition, scalar multiplication, satisfying those 8 properties given, is said to be a vector space. Any subset W of V is said to be a subspace if it is non-empty, if it contains 0 vector of V, and it is closed under vector addition and scalar multiplication. With these 3 properties, W itself is a vector space and it is a subset, hence it is said to be a subspace of the vector space V. This is all about vector subspace. Next is dependency. What is a vector? Here, if V is a vector space, then any if V is a vector space and any element, then for all V belonging to V, V is a vector. V is a vector. Okay, so we got some idea regarding vectors. Now that is, any element of a vector space is a vector. Next question is, what do we mean by dependency or independency? Two vectors V1 and V2 are linearly dependent if they are scalar multiple of each other. If they are scalar multiple of each other, then they are linearly dependent, because if I change one vector, then automatically another vector will change. Suppose V1 is equal to 5V2. So if I change my V2, automatically V1 will change. That is, V1 is depending on V2. Similarly, V2 is equal to 7V1, or here in this case, V2 is equal to 1 by 5 V1. So if I change my V1, then V2 will change. So for example, 1, 2, 3, 2, 4, 6, these are two linearly dependent vectors, because this vector into 2 gives me the second vector. First vector into 2 gives me the second vector. Next is, what about independent? Two vectors are independent, that implies they don't have any linear relation between them. For example, 1, 2, 3, 5, 4, 7. So here, this is my V1, this is my V2. Now, there is no scalar multiple relation between them. So in this case, these are linearly independent. V1 and V2 are linearly independent because they don't have any relation between them, linear relation between them. Now, if I have several vectors, suppose I have a set of vectors V1, V2 and so on up to Vn. This set is said to be each Li, I can tell like this, or I can tell V1, V2 and so on, Vn are linearly dependent. Linearly dependent if if and only if, definitions are always if and only, if one of the vector can be written as a linear combination of other vectors. If one of the vector can be written as a linear combination of other vectors, then the vectors are linearly dependent or the set is linearly dependent. For example, if I have a set of vectors 1, 2, 3, 5, 11, 9, 6, 6.5, 6. These are three vectors. This is vector 1, vector 2, vector 3. Now, this set of vectors or these three vectors are linearly dependent because these two addition is equal to twice of this, or half of this vector plus half of this vector is equal to this vector. Or also I can write that V1 plus V2 minus 2V3 is equal to 0. So here at least one of the coefficient of Vi's is non-zero. Such a combination is said to be non-trivial linear combination. If all of them are 0, then it is said to be trivial combination. So another definition of linearly independent, that is V1, V2 and so on, Vn are linearly independent if and only if C1 V1 plus C2 V2 and so on Cn Vn is equal to 0 implies C1 is equal to C2 and so on is equal to Cn, all are 0. Only under this condition, when each of the coefficient is 0, naturally each vector will be a 0 vector and sum of 0 vectors is again 0 vector. So then left hand side will be 0 vector, right hand side is equal to 0. So this is possible. If this is the only possible value of C1 to Cn, C1, C2, C3 up to Cn, if all of them are 0, that only imply that the linear combination is 0. That means there exists no non-trivial linear combination between the vectors which can be equated to 0. In that case, it is said to be linearly dependent. If there exists one non-trivial linear combination between the vectors v1 to vn which can be equated to 0, then it is linearly dependent. For example, suppose here V1 coefficient C1 is 1, C2 is 1 and C3 is minus 2. If out of all these n number of scalars, at least one is non-zero, then the linear combination is non-trivial. And if any non-trivial linear combination of the vectors can be equated to 0, then they are LD, linearly dependent, or else they are linearly independent. So these are all possible definitions of linearly dependency and independency. Next, we will discuss about rank of a matrix. Suppose I have a matrix A 1, 2, 3, 4, 2, 5, 5, 4, 8. This is the matrix. So here, how many number of linearly independent row vectors or column vectors exist? So here, these two vectors are linearly independent because there is no scalar can give me this first row vector into a scalar gives me second. There exists no such C. So they are linearly independent. But what about third case? Observe 1 plus 4 is equal to 5. 2 plus 2 is equal to 4. 3 plus 5 is equal to 8. That means third row is a linear combination of first and second row. That means this matrix is singular, and if the matrix is singular, then the vectors are linearly dependent. So here how many vectors are maximum, how many vectors are linearly independent? So this is one independent vector, this is a combination of two independent vectors. So here 1, here 2. Which one is maximum? Naturally 2. So in this case rank of A is equal to 2. So what is the original definition of rank? Rank of S matrix A is the maximum number of linearly independent row or column vectors present in the matrix. It is original definition of rank. But how to calculate it? How to calculate rank of a matrix? Suppose I have a matrix A. I have a matrix A. I will apply elementary row operations on A so that below the pivots in the pivot columns all entries will be 0. First condition is below the pivots in the pivot columns all entries will be 0. Second thing, all the 0 rows are at the bottom. Then I will get a matrix that is called echelon form of a matrix. Okay, so this is echelon form. Is echelon form. So apply elementary row operations on A to get its echelon form. What is to be done? What is the meaning of echelon form? Below the pivots in the pivot columns of the matrix U, all the elements must be 0. Second condition, all the 0 rows are at the bottom. With these two conditions, and also another condition is k plus 1th pivot must be at the right of kth pivot. And there's for each row and each column, at most one pivot can be possible, either no pivot or one pivot. But one row or one column cannot contain more than one pivots. So these are the conditions that a matrix should possess. Whenever any matrix having these conditions satisfied, then that matrix is said to be the echelon form of the given matrix. For example, let us find out its echelon form. So what I will do? In this matrix, I will do the operations I want to calculate. So what I will do the row operations. What row operations I will do? What is my first pivot? What is my first pivot? This is my first pivot. What should I do? I should make all the elements below the first pivot 0. So R2 minus 4 R1 stored in R2. Another is R3 minus 5 R1 stored in R3. Let us do these operations on my given matrix. So 1, 2, 3, first row has no effect of these two operations. So it is remaining as it is. 4 times 8, 2 minus 8, minus 6, 5 minus 12, that is minus 7. Now here it is 0, 5 times, so 4, minus 6, and here it is 5 times 15, 8 minus 7. So it is minus 7. What will be my next step? My second pivot is this one. Below it I will make 0. So what to do? R3 minus R2 stored in R3. So I got 1, 2, 3, 0, minus 6, minus 7, 0, 0, 0. So the 0 row is at the bottom. There are 2 pivots. These are 2 pivots. So maximum 2 number of linearly independent vectors are possible for this matrix. That is, rank of the matrix is number of pivots in the echelon form. So here what is the rank? How many pivots we got? Rank of A is equal to 2. What is rank of A? How to calculate rank of A? There are several ways of calculating, but at present we will go according to the book. We will refer rank of a matrix is equal to number of pivots in the echelon form of A. In the echelon form of A. Echelon form means it is an upper triangular matrix U. Okay, almost an upper. If it is rectangular matrix, it will not be an upper triangular matrix. Okay, so below the pivots, all the elements in the pivot columns are 0 and all the 0 rows are at the bottom. These two conditions satisfying matrix is said to be in echelon form. So I will reduce my A into its echelon form and I will count the number of pivots. It will give me rank. Okay, so how to verify now? What are the different applications of rank? One of the most significant application of rank is to verify linearly dependency or independency of vectors. Now in this matrix, what is the rank? Already we have calculated. So here, what is the rank of this matrix? It is 2. How to calculate rank of a matrix? We got it. Now, for example, now let us verify dependency, independency. Suppose I have 3 vectors v1, v2 and v3. So I will verify whether they are linearly dependent or independent. What I should do? I will make a matrix with v1, v2, v3 as its row vectors, or v1, this column, this is this row, this row, this row, or v1 column, v2 column and v3 column as column vectors. I'll write the given vectors as rows or columns of a matrix. Then I will convert this I will convert this matrix to its echelon form. I will convert it by applying elementary row operations. Then I will encircle the pivots. I will encircle the pivots and number of pivots will give me rank of the given matrix. Rank of A is equal to number of pivots in the echelon form of A. So I got my rank. Now there are 2 possibilities because 3 columns are there or 3 rows are there, and as I have told, in a row or column exactly at most 1 pivot is possible. That is, that in any row or any column more than 1 pivots are not possible. So now what I will do, this rank of A is always less or equal to number of vectors. Always it is either less or equal. Suppose rank of A is equal to R. Suppose number of vectors is equal to N. Now R equal to N implies and implied by the vectors are linearly independent. R is less than N implies and implied by the vectors are linearly dependent. Okay, we got some idea regarding vector space, vector subspace, linearly dependency, independency. In the next video, we will discuss about basis. Then finally, we will do problems related to this. 4 fundamental spaces and their basis and complete solution. Regarding this, we will discuss in our next video, after which we will do all the problems. Thank you for your patient listening.